We have delayed matrices for a while. Congratulations! The rectangular arrays of numbers have finally arrived. Today we define the matrix of a linear map with respect to chosen bases. And then explain how matrix vector multiplication is really just coordinate bookkeeping. Let T be a linear map from V to W. Choose a basis B of V and a basis C of W. The matrix of T with respect to B and C is built column by column. Column J is the coordinate column of T applied to Vj, written in the basis C. If V has dimension n and W has dimension m, this gives an m by n matrix. So a matrix is not the linear map itself. It is the coordinate description of the linear map after we choose bases. Tiny detail. Huge source of future suffering. Here is a simple example using the standard basis of R2. Define T of x, y to be 2x plus y, x minus y. The standard basis vectors are E1 equals 1, 0, and E2 equals 0, 1. Apply T to E1. We get 2, 1. Apply T to E2. We get 1, negative 1. Those outputs become the columns of the matrix. First column 2, 1. Second column 1, negative 1. A vector also gets a coordinate column once we choose a basis. If B is a basis V1 through Vn, then every vector V has a unique expression using that basis. If V equals A1 V1 plus through AN Vn, then the coordinate column of V with respect to B is the column of those coefficients. The vector is geometric or abstract. The coordinate column is what it looks like after choosing a basis. Mathematics. Now with costumes. Why did we wait until now to talk about matrices? Because many important properties of linear maps do not depend on choosing a basis. Injectivity, surjectivity, null space, range, rank nullity, and invertibility are not secretly about one favorite coordinate system. Later, we will meet more properties like that. But matrices are extremely convenient for actual computation. Refusing to use them forever would be mathematically pure and practically annoying. A classic combination. Now let us slow down and explain why AX is computed the way it is. A has m rows and n columns. The vector x has n entries. The matching number n is not decoration. It tells us each row of A can pair with every entry of x. Since A has m rows, the output AX has m entries. So before doing arithmetic, we already know the shape. M by 1. Tiny victory. Try not to celebrate too loudly. The cleanest way to understand the formula is to think of A by columns. Write the columns of A as C1, C2, through Cn. The entries of X are X1, X2, through Xn. Then AX means, use the entries of X as weights, and form X1 C1 plus X2 C2, plus all the way to Xn Cn. So AX is not magic row machinery yet. It is first a linear combination of the columns of A. Now expand that column combination, and the usual row formula appears. Each column Cj has entries A1j, A2j, down to AMJ. When we multiply each column by its matching X entry and add the columns, we add vertically. Now let us write the result entry by entry, without cramming 3 civilizations onto one screen. The first output entry collects the first entries from all columns. The second output entry collects the second entries from all columns. That is why the first row of A combines with X. Then the second row combines with X. And so on. The row formula is just the column combination written entry by entry. Now we can state the fast computational rule. For entry I of AX, use row I of A. Multiply across with x1 through xn, then add. That gives one entry of the output. Repeat for every row. Tedious? Yes. Mysterious? Not anymore. Lower your standards and enjoy progress. Here is a concrete example. Take A equal to the matrix with columns 2, 1 and 1, -1. Take X equal to the column vector 3, 4. Multiply A by X using row.column. The first entry is 2 times 3 plus 1 times 4. The second entry is 1 times 3 plus -1 times 4. So AX is 10, -1. Now connect this calculation back to the linear map. The key formula is coordinate column of T of V equals the matrix of T times the coordinate column of V. The input coordinates use the basis B. The matrix describes T relative to B and C. The output coordinates use the basis C. That is the real meaning of matrix vector multiplication. It is not random arithmetic. It is the coordinate version of applying a linear map. Let us summarize before the matrices start multiplying and pretending this was inevitable. The matrix of a linear map depends on the bases we choose. A coordinate column is a vector written relative to a chosen basis. Matrix vector multiplication is computed by row.column. Conceptually, matrix vector multiplication is applying a linear map after translating everything into coordinates. Next time, we discuss matrix addition and matrix multiplication. Because apparently one rectangular grid was not enough.